Well, at the moment, our task is to determine y equals cosine of x is odd, even, or neither. And a function is even if f of negative x equals f of x. It's odd if f of negative x equals negative times f of x. And if neither of these conditions are satisfied, then the function is neither odd nor even. So for y equals cosine of x, we know that cosine of negative x equals cosine of x. And that satisfies the criteria for an even function, so y equals cosine of x is even. It's an even function. And that was the first one. Number 2, we've got to determine from the graph whether f of x equals e to the x on the interval x is less than or equal to 0, and x minus 2 quantities squared on the interval x is greater than 0. We've got to determine if that function is 1 to 1. So we'll go ahead and graph it. And now, for f of x equals e to the x, with the domain x is less than or equal to 0, we'll graph that. Here's what it graphs like, and the y-intercept is at 0, 1, because e to the 0 is 1. Now, for the next part of the function, the second piece, x minus 2 quantities squared. Well, if f of x equals x minus 2 quantities squared, then the value of x that takes that to 0 is 2. Occurs at 2, 0. No. 2, 0. And if we let x be 0, we get negative 2 squared, which is 4. And I'm going to put an open circle here because x can get infinitely close to 0, and as it does so, y will get infinitely close to 4, but it will never get there exactly. So we're at 0, 4. And so the graph looks like this. Now, the question is, does this function satisfy the, or is it 1 to 1? Well, to be 1 to 1, it must satisfy the horizontal line test. And I'll draw a horizontal line, and notice that horizontal line intersects this graph in 2 places. We just had to find where the horizontal line test, one incidence where it wasn't satisfied, and in so doing we know that f of x is not 1 to 1. And we're done with this question. Now for question 3, we have to isolate y. And to do that, we'll employ the definition of the natural logarithm, which is y equals ln of x if and only if e to the y equals x, where y is the exponent, x is the result. So for a, we have ln of 1 minus 2y equals t. So the dilemma is we need to release this 1 minus 2y from the logarithmic function. To do that, we'll rewrite this equation in exponential form. So the result is 1 minus 2y, and the exponent is t. Now let's Subtract e to the t from both sides and add 2y to both sides. So 1 minus e to the t then equals adding 2y to both sides, 2y. Now I'm going to exchange positions, so we have 2y equals 1 minus e to the t. And to isolate y, we'll divide both sides by 2. So now y equals 1/2 times 1 minus e to the t. And in this case, we've isolated y, so this side's done. Now let's do b. And we have e to the ky equals x. Now the problem is that the ky is in the exponent position. We have to release this ky from that position and put it in a standalone position. To do that, we'll rewrite this equation in logarithmic form. So the exponent is ky, and the result is x, so ln of x. Now, to isolate y, we'll divide both sides by k. The k's divide out, and we get y equals 1 over k ln of x. One final step, employing a law of logs, we can write that this as ln of x to the 1 over k. And we've isolated y, so we're done.